Optical coherence tomography, Acht, is an imaging technique that uses coherent light to capture micrometer resolution, 2- and 3-dimensional images from within optical scattering media, e.g., biological tissue. It is used for medical imaging and industrial nondestructive testing, NDT. Optical coherence tomography is based on low-coherence interferometry, typically employing near-infrared light. The use of relatively long wavelength light allows it to penetrate into the scattering medium. Confocal microscopy, another optical technique, typically penetrates less deeply into the sample but with higher resolution. Depending on the properties of the light source, superluminescent diodes, ultra-short pulsed lasers, and supercontinuum lasers have been employed. Optical coherence tomography has achieved sub-micrometer resolution, with very wide spectrum sources emitting over a 100 nm wavelength range. Optical coherence tomography is one of a class of optical tomographic techniques. A relatively recent implementation of optical coherence tomography, frequency domain optical coherence tomography, provides advantages in signal-to-noise ratio, permitting faster signal acquisition. Commercially available optical coherence tomography systems are employed in diverse applications, including art conservation and diagnostic medicine, notably in ophthalmology and optometry, where it can be used to obtain detailed images from within the retina. Recently, it has also begun to be used in interventional cardiology to help diagnose coronary artery disease. It has also shown promise in dermatology to improve the diagnostic process. Introduction. Starting from white light interferometry for in vivo ocular eye measurements, imaging of biological tissue, especially of the human eye, was investigated by multiple groups worldwide. A first two-dimensional in vivo depiction of a human eye fundus along a horizontal meridian based on white light interferometric depth scans was presented at the ICO 15 SAT conference in 1990. Further developed in 1990 by Naohiro Tano, then a professor at Yamagata University, and in particular since 1991 by Huang et al., in Professor James Fujimoto Laboratory at Massachusetts Institute of Technology. Optical coherence tomography, Acht, with micrometer resolution and cross-sectional imaging capabilities has become a prominent biomedical tissue imaging technique. It is particularly suited to ophthalmic applications and other tissue imaging requiring micrometer resolution and millimeter penetration depth. First in vivo Acht images displaying retinal structures were published in 1993 and first endoscopic images in 1997. Acht has also been used for various art conservation projects, where it is used to analyze different layers in a painting. Acht has interesting advantages over other medical imaging systems. Medical ultrasonography, magnetic resonance imaging, MRI, confocal microscopy, and Acht are differently suited to morphological tissue imaging, while the first two have whole body but low resolution imaging capability, typically a fraction of a millimeter. The third one can provide images with resolutions well below 1 micrometer, i.e. subcellular, between 0 and 100 micrometers in depth, and the fourth can probe as deep as 500 micrometers, but with a lower, i.e. architectural, resolution. Around 10 micrometers in lateral and a few micrometers in depth in ophthalmology, for instance, and 20 micrometers in lateral in endoscopy. Acht is based on low coherence interferometry. In conventional interferometry with long coherence length, i.e., laser interferometry, interference of light occurs over a distance of meters. In Acht, this interference is shortened to a distance of micrometers, owing to the use of broad bandwidth light sources, i.e., sources that emit light over a broad range of frequencies. Light with broad bandwidths can be generated by using superluminescent diodes or lasers with extremely short pulses, femtosecond lasers. White light is an example of a broadband source with lower power. Light in an Acht system is broken into two arms: a sample arm, containing the item of interest, and a reference arm, usually a mirror. The combination of reflected light from the sample arm and reference light from the reference arm gives rise to an interference pattern, but only if light from both arms have traveled the same optical distance, same meaning a difference of less than a coherence length. By scanning the mirror in the reference arm, a reflectivity profile of the sample can be obtained. this is time domain Acht. Areas of the sample that reflect back a lot of light will create greater interference than areas that don't. Any light that is outside the short coherence length will not interfere. This reflectivity profile, called an A-scan, contains information about the spatial dimensions and location of structures within the item of interest. A cross-sectional tomograph, B-scan, may be achieved by laterally combining a series of these axial depth scans, A-scan. A-face imaging at an acquired depth is possible depending on the imaging engine used. Layperson's explanation. Optical coherence tomography, or Acht, is a technique for obtaining subsurface images of translucent or opaque materials at a resolution equivalent to a low-power microscope. It is effectively optical ultrasound, imaging reflections from within tissue to provide cross-sectional images. Acht has attracted interest among the medical community because it provides tissue morphology imagery at much higher resolution, better than 10 than other imaging modalities such as MRI or ultrasound. The key benefits of Acht are: live subsurface images at near microscopic resolution, instant, direct imaging of tissue morphology, no preparation of the sample or subject, no ionizing radiation. Acht delivers high resolution because it is based on light, rather than sound or radio frequency. An optical beam is directed at the tissue, and a small portion of this light that reflects from subsurface features is collected. Note that most light is not reflected but, rather, scatters off at large angles. In conventional imaging, this diffusely scattered light contributes background that obscures an image. However, in Acht, a technique called interferometry is used to record the optical path length of received photons, allowing rejection of most photons that scatter multiple times before detection. Thus Acht can build up clear 3D images of thick samples by rejecting background signal while collecting light directly reflected from surfaces of interest. Retinal layer segmentation of macular Acht. Retinal layer segmentation of macular Acht. Within the range of non-invasive three-dimensional imaging techniques that have been introduced to the medical research community, Acht as an echo technique is similar to ultrasound imaging. Other medical imaging techniques such as computerized axial tomography, magnetic resonance imaging, or positron emission tomography do not use the echolocation principle. The technique is limited to imaging 1 to 2 mm below the surface in biological tissue, because at greater depths the proportion of light that escapes without scattering is too small to be detected. No special preparation of a biological specimen is required, and images can be obtained non-contact or through a transparent window or membrane. It is also important to note that the laser output from the instruments is low. Safe near-infrared light is used and no damage to the sample is therefore likely. Theory. The principle of Acht is white light, or low coherence, interferometry. The optical setup typically consists of an interferometer, Fig. 1, typically Michelson type, with a low coherence, broad bandwidth light source. Light is split into and recombined from reference and sample arm, respectively. Time domain. In time domain Acht, the path length of the reference arm is varied in time, the reference mirror is translated longitudinally. A property of low coherence interferometry is that interference, i.e. the series of dark and bright fringes, is only achieved when the path difference lies within the coherence length of the light source. This interference is called autocorrelation in a symmetric interferometer. Both arms have the same reflectivity, or cross-correlation in the common case. The envelope of this modulation changes as path length difference is varied, where the peak of the envelope corresponds to path length matching. Frequency domain. In frequency domain Acht, FD Acht, the broadband interference is acquired with spectrally separated detectors, either by encoding the optical frequency in time with a spectrally scanning source or with a dispersive detector, like a grating in a linear detector array. Due to the Fourier relation, Wiener-Kinshine theorem between the autocorrelation and the spectral power density, the depth scan can be immediately calculated by a Fourier transform from the acquired spectra, without movement of the reference arm. This feature improves imaging speed dramatically, while the reduced losses during a single scan improve the signal-to-noise ratio proportional to the number of detection elements. The parallel detection at multiple wavelength ranges limits the scanning range, while the full spectral bandwidth sets the axial resolution. Spatially encoded. Spatially encoded frequency domain Acht, SEFD Acht, spectral domain, or Fourier domain Acht, extracts spectral information by distributing different optical frequencies onto a detector stripe, line array CCD or CMOS, via a dispersive element, see Fig 4. Thereby the information of the full depth scan can be acquired within a single exposure. However, the large signal-to-noise advantage of FD-Oct is reduced due to the lower dynamic range of stripe detectors with respect to single photosensitive diodes, resulting in an SNR, signal-to-noise ratio, advantage of 10 dB at much higher speeds. This is not much of a problem when working at 1300 nm, however, since dynamic range is not a serious problem at this wavelength range. The drawbacks of this technology are found in a strong fall-off of the SNR, which is proportional to the distance from the zero delay, and a sin-type reduction of the depth-dependent sensitivity because of limited detection line width. 1 pixel detects a quasi-rectangular portion of an optical frequency range instead of a single frequency. The Fourier transform leads to the sin-Z behavior. Additionally, the dispersive elements in the spectroscopic detector usually do not distribute the light equally spaced in frequency on the detector, but mostly have an inverse dependence. Therefore, the signal has to be resampled before processing, which cannot take care of the difference in local, pixel-wise, bandwidth, which results in further reduction of the signal quality. However, the fall-off is not a serious problem with the development of new generation CCD or photodiode array with a larger number of pixels. Synthetic array heterodyne detection offers another approach to this problem without the need for high dispersion. Time-encoded. Time-encoded frequency domain Oct, TEFD Oct, or swept source Oct, tries to combine some of the advantages of standard TD and SEFD Oct. Here the spectral components are not encoded by spatial separation, but they are encoded in time. The spectrum is either filtered or generated in single successive frequency steps and reconstructed before Fourier transformation. By accommodation of a frequency scanning light source, i.e. frequency scanning laser, the optical setup, see Fig 3, becomes simpler than SEFD. But the problem of scanning is essentially translated from the TD-Oct reference arm into the TEFD-Oct light source. Here the advantage lies in the proven high SNR detection technology, while swept laser sources achieve very small instantaneous bandwidths, line widths, at very high frequencies, 2200 kHz. Drawbacks are the nonlinearities in the wavelength, especially at high scanning frequencies, the broadening of the line width at high frequencies, and a high sensitivity to movements of the scanning geometry or the sample, below the range of nanometers within successive frequency steps. Full field Oct. An alternative approach to temporal and frequency Oct was developed by Claude Baccarat's team in 1998, with an acquisition of the images without beam scanning. In this technique called full field Oct, FF Oct, unlike other Oct techniques that acquire cross-sections of the sample, the images are here en-face, i.e. like images of classical microscopy, orthogonal to the light beam of illumination. More precisely, interferometric images are created by a Michelson interferometer where the path length difference is varied by a fast electric component, usually a piezo mirror in the reference arm. These images acquired by a CCD camera are combined in post-treatment, or online, by the phase shift interferometry method, where usually 2 or 4 images per modulation period are acquired, depending on the algorithm used. The en-face tomographic images are thus produced by a wide-field illumination, ensured by the Linux configuration of the Michelson interferometer where a microscope objective is used in both arms. Furthermore, while the temporal coherence of the source must remain low as in classical Oct, i.e. a broad spectrum, the spatial coherence must also be low to avoid parasitical interferences, i.e. a source with a large size. Scanning schemes. Focusing the light beam to a point on the surface of the sample under test, and recombining the reflected light with the reference will yield an interferogram with sample information corresponding to a single A scan, Z-axis only. Scanning of the sample can be accomplished by either scanning the light on the sample, or by moving the sample under test. A linear scan will yield a two-dimensional data set corresponding to a cross-sectional image, XZ-axis scan, whereas an area scan achieves a three-dimensional data set corresponding to a volumetric image, XYZ-axis scan, also called full-field Acht. Single point systems based on single point, confocal, or flying spot time domain Acht, must scan the sample in two lateral dimensions and reconstruct a three-dimensional image using depth information obtained by coherence gating through an axially scanning reference arm, Fig. 2. Two-dimensional lateral scanning has been electromechanically implemented by moving the sample using a translation stage, and using a novel microelectromechanical system scanner. Parallel or full-field Acht using a charge-coupled device, CCD, camera has been used in which the sample is full-field illuminated and end-face imaged with the CCD, hence eliminating the electromechanical lateral scan. By stepping the reference mirror and recording successive end-face images, a three-dimensional representation can be reconstructed. Three-dimensional Acht using a CCD camera was demonstrated in a phase-stepped technique, using geometric phase shifting with a Linux interferometer, utilizing a pair of CCDs and heterodyne detection, and in a Linux interferometer with an oscillating reference mirror and axial translation stage. Central to the CCD approach is the necessity for either very fast CCDs or carrier generation separate to the stepping reference mirror to track the high-frequency Acht carrier. Smart detector array. A two-dimensional smart detector array, fabricated using a 2M complementary metal oxide semiconductor, CMOS, process, was used to demonstrate full-field TD Acht featuring an uncomplicated optical setup, Fig. 3. Each pixel of the 58x58 pixel smart detector array acted as an individual photodiode and included its own hardware demodulation circuitry. Selected applications. Optical coherence tomography is an established medical imaging technique and is used across several medical specialties including ophthalmology and cardiology, and is widely used in basic science research applications. Ophthalmology. Acht is heavily used by ophthalmologists to obtain high-resolution images of the eye's anterior segment and retina. Owing to its cross-sectional capabilities, Acht provides a straightforward method of assessing axonal integrity in multiple sclerosis and glaucoma. Acht is also well suited to assess macular degeneration, and is considered the new standard for the assessment of diabetic macular edema. More recently, ophthalmic Acht devices have been engineered to perform angiography, and have been used to assess retinal microvasculature pathology in diseases such as glaucoma and diabetic retinopathy. Cardiology. In the setting of cardiology, Acht is used to image coronary arteries in order to visualize vessel wall lumen morphology and microstructure at a resolution 10 times higher than other existing modalities such as intravascular ultrasounds and X-ray angiography, intracoronary optical coherence tomography. For this type of application, approximately 1 mm in diameter fiber optics catheters are used to access artery lumen through semi-invasive interventions, i.e. percutaneous coronary intervention. The first demonstration of endoscopic Acht was reported in 1997, by researchers in James Fujimoto Laboratory at Massachusetts Institute of Technology, including Professor Guillermo James Tunney and Professor Brett Bauma. The first TD Acht imaging catheter and system was commercialized by Lightlab Imaging, Inc., a company based in Massachusetts in 2006. The first FD Acht imaging study was reported by the laboratory of Professor Guillermo James Tunney and Professor Brett Bauma based at Massachusetts General Hospital in 2008. Intravascular FD Acht was first introduced in the market in 2009 by Lightlab Imaging, Inc. and Terumo Corporation launched a second solution for coronary artery imaging in 2012. The higher imaging speed of FD Acht enabled the widespread adoption of this imaging technology for coronary artery imaging. It is estimated that greater than 100,000 FD Acht coronary imaging cases are performed yearly, and that the market is increasing by approximately 20% every year. Recent developments of intravascular Acht included the combination with other optical imaging modalities. Acht has been combined with fluorescence molecular imaging to enhance its capability to detect molecular/functional and tissue morphological information at the same time. In a similar way, combination with near-infrared spectroscopy has been also demonstrated. Oncology. Endoscopic Acht has been applied to the detection and diagnosis of cancer and precancerous lesions, such as Barrett's esophagus and esophageal dysplasia. Research applications. Researchers have used Acht to produce detailed images of mice brains, through a window made of zirconia that has been modified to be transparent and implanted in the skull. Optical coherence tomography is also applicable and increasingly used in industrial applications, such as non-destructive testing, NDT, material thickness measurements, and in particular thin silicon wafers and compound semiconductor wafers thickness measurements, surface roughness characterization, surface and cross-section imaging and volume loss measurements. Acht systems with feedback can be used to control manufacturing processes. With high-speed data acquisition and submicron resolution, Acht is adaptable to perform both inline and offline. Due to the high volume of produced pills, an interesting field of application is in the pharmaceutical industry to control the coating of tablets. Fiber-based Acht systems are particularly adaptable to industrial environments. These can access and scan interiors of hard-to-reach spaces, and are able to operate in hostile environments whether radioactive, cryogenic, or very hot. Novel optical biomedical diagnostic and imaging technologies are currently being developed to solve problems in biology and medicine. As of 2014, attempts have been made to use optical coherence tomography to identify root canals in teeth, specifically canal in the maxillary molar. However, there's no difference with the current methods of dental operatory microscope. Research conducted in 2015 was successful in utilizing a smartphone as an Acht platform, although much work remains to be done before such a platform would be commercially viable.
Please subscribe and thanks for watching.